This is the 2.4 steel design per AISC 360. I'll cover both 360 05 and 010 and some of the differences between the two codes. This one will cover mostly just member design. So it will be chapter B, C, E, F, H, D, and J. J will be saved till the next presentation, but we'll cover some of these: introduction, what's the Y flange shape, and how do we call out, and what they are, followed by all the different design sections in 360. Like I pointed out before, IBC, how IBC and AISC 360 related is 2009 IBC references the 13th edition. The 2012 IBC references the 14th edition. So for those building jurisdictions that have not adopted the 2012, which a lot of them have not, they will be in the 13th edition. I believe California is starting to do the 2012 starting next year. So once they adopt it, the 14th edition comes into play. For our design, the design is very minimal in terms of the difference between the two design editions. I'll point out some of the differences now. The differences between 360.05 and 360.10, from the fluctuate section, the C sub B value changed a little bit. In this, what we'll be doing is we're going to be using SAP. So the version I have right now, it only covers 2005. But when we're going to purchase the newest SAP, I believe version 15, then they'll have both options of 2010 and 2005 as well. So all you have to do is simply switch the design section in SAP, and you're covering it per the 360.10. Another big change which we are taking advantage of is the bolt strengths are higher in the 2010. So they did more testing. The shear capacities are actually higher in the 2010 versus the 2005. In the 2010 they separated into groups now in terms of the bolt. Group A and Group B. Essentially, Group A is kind of normal strength. Group B is high strength. Yeah, that's right. Here are some of the capacities for 2010. Differences you can see from 2005, comparison between 2005 and 2010, where you have a high, you're getting an increase in terms of the shear stress, from 60 to 68 KSI. So these are the ones we are using. The 490. When we get into the design of the connection, I'll tell you which grade of bolt we're using, where we're using them. But mainly we're using the A325, A490. So we're using both types, and you can see both of them are increased. And this is the threads are not included. So you see the differences. They're pretty much the same increase from both of them. The W shapes, I think you guys are somewhat familiar with it, and here's just a copy from the table. So the table lists the shape designations first, so increase from the W12 or W10 and all the way increases up, so that goes to W36 or W something, whatever it stops. So in each column after that you have the area, the depth, so it's defined as this. The thickness of the web, that's the TW. TW divided by 2. Thickness of the flange width. The flange thickness. I think this one, flange thickness. And then some other K area for when you're working with bolts and clearing the K area. And then workable gauges, followed by your compact section criteria. They actually do the calculations for you, B over 2T and H over TW. All these are actually listed in the manual, so you don't really need to do it. And then the property around the axis, the x-axis, y-axis, torsional constant, and so on, which is cut off on this side. So some of the we're, like I said, we're currently limited to W16, W18, and half-inch link thickness. I keep hammering it in. We do have a Excel database that covers the 14. So, and I have included that in the training. So we could just do Excel VLOOKUP to look up those properties instead of having to go to the table and look up each time. Some of the properties, like I say, point out are important is the depth, the flange width, the flange thickness, the web thickness, moment inertia in the x-axis, plastic section modulus in the x-axis, SX, and then RY radius gyration in the weak axis. When we mentioned W14 by 132, like the one on the top, typically the first one is a nominal depth. It's 14 inch. You can see the 14 inch, 14.7, 14.5, 3, 2, 0. So it varies a little bit, but is in the 14 range. And then the second number at 132 is the weight per foot. So the 132 is if you have cut a section of beam, you try to carry it. That's 132 pounds. So that's how we distinguish these. So typically, steel, what they do is the cost is a lot of them are still related to the weight. So when you're trying to design the building, you're trying to optimize or design it to be as light as possible, if you can. And that's a lot of people price on that. The tonnage of steel is how much they weigh and how much they quote people. Yeah. But sometimes if you have a lot of different sections, handling different sections becomes costly. You would like to reduce it to certain sections if possible. So, but the rule number one is try to keep the shape when you're doing the design to be as light as possible, because that's what they price it in. They price the steel is the weight weight of the steel. However, obviously, the deeper itself, you get better capacity and lighter, but you might not be able to fit the column or fit the beam. So those are some of the design concerns as well. Chapter B, let me start out with B is the classification of section for local buckling. And I'll show you some pictures what I mean by local buckling before. All these B over T ratios, they have the compact, non-compact, and spell out in each case. This is for unstiffened elements, and they have one for stiffened elements, so they're separated now. So yeah, this is stiffened elements, they're unstiffened elements. So when you're doing design, you would have to check where you are, and then which case you fall under. Then when you go to the different sections, they'll tell you which design equation to use, essentially. Here are some examples of local buckling. So B over T, you need this one is local buckling, and for the tube, all these are local buckling. So since these are actually dissipating energy, the B over T is not from 360. The B over T actually from 341.05 or 4110, whatever code they're designing to. So it's a little bit more stringent for us, because we're not yielding, because we never get to this. The flanges don't yield. Our B over T is per 360. So per these two tables. Why is it important? If you look at this curve, keep looking at the curve, moment rotation, capacity of the moment MP up here. If you have a B over T that is small, you are most likely to get to your MP. However, if you keep increasing the B over T, you don't get to the MP. Okay, because you're buckling prematurely at that time. You're buckling, so you're only getting in this one showing it, you're only getting half the capacity. So B over T, you're trying to get what people say is compact section. The compact is a smaller number, the better. So that's the importance of B over T on flexure and ductility, on local buckling. This is another way of showing it. Your ductility, your moment capacity. Lambda R is related to the B over T. Lambda P is plastic. So the bigger itself, the less moment you're going to get. Chapter C. So basically that's chapter B. Chapter B is just two charts there. they're going to tell you what's the BOT requirement for each of the cases you meet, and you just check it. They give you basically gives you the limit of what the BOT is. Chapter C is on stability analysis and design. It tells you the methods of analysis to use, which one you want to choose, and what are some of the options you have. So they're basically group it into two types. You have the effective link method, that's the K calculation, and you have the direct analysis method. This one is relatively new. It's introduced in 2000. It's in the appendices 2005, but they move it up front in 2010. So this now is a preferred way of doing it versus this. But sometimes it doesn't really make sense to us to adopt this, and I'll show you why that is in a couple of slides. So, like I said, the effective link on the method is on chapter C in 2000 in the Black Book. Direct analysis was in Appendix 7. In the 2010, they flipped the two. They moved that one from the appendices to become a main chapter, and then the other one back to the appendices 7. Which means is this is the main body, so that's the preferred method of calculating the K. That's what they wanted you to use. Here is the BOT for the per 341. So as you can see, it's a lot more stringent than the other ones. Before you could see 1 point something, now it's only 0.3. So the ratio is a lot more smaller to get a compact. Typically, moment connections where the beam is diffused, they must meet this ratio. Okay, the R beams and columns are not yielding. We don't need to meet this ratio. We only have to meet the 360. Stability and design continuing. This is C1. Basically, what they tell you to do is you have to consider all of the effects on the structure. So flexural shear and axial member deformations must be contributed to the calculation of displacement of the structure. Second order effects, both P delta and P small delta, and their difference I'll show you later. What's the difference between the big one and small delta? You have to consider geometric imperfections, stiffness reduction due to inelasticity, uncertainty in stiffness and strength. So you have to account for all these requirements when you're doing analysis. They spell it out in chapter C. That's a stability requirement. Big delta, when you talk about second order effect, P delta versus small delta. Big P delta, it affects the global behavior. So this is the whole behavior. Small delta is just on the element itself. It's curvature. When you curve it, you get the P delta. This one is on the whole frame. Geometric imperfections. When you fabricate a certain beam, a certain column, there are some tolerances they give you. You cannot be perfectly straight. So that's our straightness. And now when you're building a structure, you don't get the full straightness either. So you're off a little bit. They call this our plumbness, and they allow E over 500 per co. So there's a lot of bowing in the shape, or when you're erecting is not taut, is not straight. That's where the imperfections are coming from. Okay, stiffness reduction. That's related to this, to the stress and strain. When you're doing a elastic design, this is elastic. Okay, so no big deal. But when you're going into the plastic range, then you're that's K, or they use a T, the E, but that K value is reducing from a high number to a smaller number when you go horizontal. So that's what they mean by stiffness reduction. Here's how to handle it. They call it a direct modeling. You model your structure with these offsets. So top tolerance because you're building it. So you model it and then you apply your load. This is a very hard way of doing it because you have to calculate how much of the structure. You don't draw your members straight. You actually draw it offset a little bit, and then apply the loads to capture your geometric imperfection. That's not the way to go, and it's very hard. It's very different for each structure if you do it that way. Another way to handle it is apply some sort of what they call a notional low. This is relatively new, and not many people are used to that yet, but notional low essentially is a portion of the gravity low you apply as a lateral low to the frame to mimic the effect of your geometric imperfection, our plumbness, or erection, our tolerance. So how to model it with this one is you take the gravity load, you multiply it by 2%, and the alpha depends on if it's an RFD or ASD. So alpha is 1 for RFD, ASD I think is 1.6. To take care of the stiffness reduction, you reduce all stiffness by 20. No, not all by 80%, but basically reduce by 20% to get to 80%, and they are contributed to stability. So assuming your structure is gone into the yielding it already, then you have to reduce your stiffness. For us, we're elastic. Reducing the stiffness don't quite make sense. Only you should be reducing it for the connection. So that's why you really can't just adopt this one like that. Now when we do SAP, I'll switch some of the analysis procedures to show you guys what some of the effects are when they talk about using this method or using that method, and you could tell the difference right away in the SAP. I tell you, the drift goes actually reducing the stiffness increases quite a bit. So that's the stiffness reduction, basically 80% EA or EI. You take 80% of it. Direct analysis. This is where you perform your analysis, the second order, and you apply your notional low, and then you do your analysis and your design. The good thing about this, because of all these effects, you don't need to calculate what K is. Previously, you look it up from the chart, you have to calculate K, and K is always greater than 1. If you include all these effects on your analysis, your K could be 1. So you don't need to worry about K. That's what's new in the direct analysis. The effective link method is where the K calculation comes in. Okay, so effective link now is Appendix 7. You still need to apply the gravity low of the notional low. The next is you perform a second order analysis, and then using your nominal stiffness, so no stiffness reduction, and you determine a K from some kind of buckling analysis. If the first order and second order are less than 1.1, then K equals 1. So for us, we're not really checking that first order, second order. There's another additional check. We'll just say let the SAP calculate a K and see what K value it is, because we have first of all we have the PR connection. We don't know what the effect of that is. So the computer program probably models it better and gets a better solution than us looking up a K value. Effective link. There's a second method. So how is it different from a direct analysis? Okay, this one we must determine the K when you're doing effective link. So you do not use the reduced stiffness, but you have to determine what K is. Here is from the SAP manual directly. They kind of organized it in a way of pretty easy to see. This is a direct analysis method. General second order analysis. What are the limitations? What are the variables? So you have to verify that the stiffness reduction, fixed stiffness. Here's second order. What are some of the differences between the two? And this is also a direct analysis. You basically amplify the first order, and you don't have no limitations when you're applying it. However, we're not going to be using the direct stiffness analysis method. We're going to be using let me finish out what the effective link is. So we also summarize the effective link here. So you essentially have 3: general second order, amplified first order, and limited first order for analysis. So you could pick any of these in SAP for the analysis, but the consequences is you have to do something more because of your assumption. Okay, so let's compare to what we want to use in our analysis and design. beam and column remain elastic due to our design procedures. We want them to be elastic, so essentially no reduction in beam and column stiffness. SEP performs a second order analysis and has the option to include a P delta. So we took care of the P delta effect. SEP also performs a general second analysis. So we took care of the second order as well. So we'll let SEP determine the K, and it's not equal to 1. So we're using the effective link method, general second order analysis, and the applicability is your second order has to be less than order by 1.5. So that's what we're using, and it's set up in the template. Just want to go through the background for you guys and see what we're doing. Chapter E is on compression design, and ours is because the symmetric section. I cut off the rest because you use like uneven sections or L shapes, angles, whatever. Only these sections apply to us. This is with cylinder elements. This is without cylinder. This is with cylinder, and that's where your QA and what is the other one? The Q comes in. Forgot what the other one. QS, QA and QS terms come in. So if you have without the cylinder elements, then you use these two sections, and if you have cylinder elements, then you have to check E7. So check if your elements are cylinder. How do you know if they're cylinder? That's where chapter B comes in. So you go to chapter B, look up the table, and then make sure you check both the web and the flange. Okay, it depends on the element's depends on what the element's cylinderness. Then you proceed to the design sections, and that's how you use 360 in XCO design. So for E3, this is pretty straightforward. You guys use that before. Plug and chuck, no big deal. If your FR is determined as this, then you use that, and then you get your XCO low. That's not a big deal. So now, for E.4, for all other case, you need to find out for doubly symmetric sections FE what FE would be. So essentially, instead of E4, you replace it with replace 4.4 for your analysis and design for E.4 and E.3. E.7, like I say, are the Q factors to capture, the post-buckling behavior, and I'll show you why they require and what the Qs are. For a typical compression, the stiffened elements take most of the stress. So it will be like this. Distribution will be like this. The cold ones that make it easy, so they ignore the center portion and lump it on either side. So basically, the stiffness, the stiffened elements would assume take all. So you would have to approximate what's the width here and what's that width. So same as for unstiffened elements, what they have is a maximum stress at the end because it's stiffened here, and non-stiffened you have a minimum stress at this end. But what they do is they take an average of the two for you to use when you're doing unstiffened design. So the Q is the net reduction factor accounting for cylinder elements and compression. And then QA times QS for the member, so you have to do both the flange and the web, and then multiply them to get your Q value. Okay, so for the flanges is the QS is stiffened, unstiffened. So basically, it depends on where they are. You give you a couple of equations to calculate. If your B over T is less than that, then you use the QS of this. If it's in between this range, you're going to use QS. So that's pretty straightforward. The web is one that's a little bit tricky, is because you have to calculate the effective area. The effective area, a gross area is just from the manual. The effective area is where you actually have to calculate what B sub E would be for the different elements. So that's it. I mean, once you put in the B sub E, then you times the thickness, then you get the effective E. Okay, so that's what QA and QS is. For fluxure, we have pretty much 4 sections to consider because we are symmetric shape. This is bending, so chapter F, the fluxure. So depends on what limit state or what slenderness. Again, it comes back to slenderness. How you use this is check your web or flange. If the flange is compact, if the web is compact, then you go to F2. If there's something else, then you go to that section. So that's how you use it. So first of all, you have to calculate where your flange falls and where your web falls in terms of the cylinders limit. Okay, so general provisions. Again, this is pretty straightforward. Here's the 2010. There is no factor after it anymore. So that's what one of the changes are. For yielding is, where we said before, the MP is Fy and Zx. That's yielding, the first one. Lateral torsional buckling depends on how what's the span and then the bracing ratio. So that's the yielding first mode. So you have to take the minimum of all these failure modes. So that will be your capacity. Just want to point out, it's a little tricky. We can't just depend on SEP for checking this one, because especially for the column. Remember, a procedure requires to replace ZX with SX because we only want to brace the top of the column. So when you're doing the SEP design, it will give you a DCR, demand capacity ratio, based on ZX. So you kind of have to go in and slightly modify it and use the ratio between the two to kind of increase the DCR ratio. And I'll show you what to do when it comes to the Excel. So that's one thing that's not quite straightforward for the protocol and just using SEP. You can't just use SEP for this one because that's a requirement of SEP. Lateral torsional buckling, like I said before, this points out it depends on where you're bracing, where you're supporting your beam or your column. LP, anything less than LP, you get the full MP capacity. However, once you pass that, then your moment is going to decrease significantly. So that's all depends on LB, LP, and LR. And to calculate these numbers, LR, LP, they give you an equation to calculate it. LB is essentially your embrace length. We know what it is from calculation. So that's F2. So LP, you get all the MP. This is, like I said, the equations to calculate LP and the equations to calculate LR are just right below the 2.4 and 2.3. So it's 2.5 is calculate LP. So plug and check again. And then remember, this was 0.08 or so for moment frame bracing. So we're basically you could tell the difference between what's required and for LP, and to get the LP distance versus the bracing. And we'll take a look at it later. Non-compact, section 3 is doubly symmetric shape with compact webs and non-compact or slender flanges. So if your section falls underneath that, then come to this section for design. 4 is compact or non-compact web. Then you go to F4 for the design. Flange bending, there are different ones. One is the compression flange yielding, one side, lateral torsion buckling, the overall, and then the compression flange buckling again. So there's more checks when you come to here. And then after the compression flange, then you check your tension flange yielding. F5 is for slender web. So once you have a slender web, then you have more requirements to meet, and capacities are typically less than what the other ones are. Tension, flange yielding, so we've seen that before. One thing that SEP would not do is that the F13 again. What's F13 is holes in the flange. Okay, so when you're modeling SEP, they assume you just the same property, right? You can't model holes in SEP. So you have to check it yourself at a certain point. So that's SEP do not check that. So you have to check your hole and include it in the analysis somehow. Okay, so the two major things is we have to modify the ZX to SX for the column check, and also for add F13 into the design as an additional check for our own because SAP 2000 do not check this limit state. Shear design, this one is relatively straightforward because we're only concentrating on G1 and G2. We're not taking the tension field action into play, and I'll tell you what it is. And the J section will cover this under the connection design because this is where it comes in under J. So, but it is also for shear. General provision, shear is very straightforward, and basically a G2, just want to reiterate, does not utilize post-buckle strength, so no tension field action. So we're not using this tension field action to add to the shear capacity. We're just basically using the basic shear capacity of the member. What that does is just 0.6 Fy area times CW, and CW depends on if you're a row shape or what, and typically CW is 1 or maximum is typically 1 for what we're doing. However, it could be something that you have to calculate, like this one. If your ratio, again, all comes back to the H/T, the slenderness of the web. If your web is compact, then your C equals 1. If you're non-compact or over that, then your C would be reduced significantly. Okay, that's shear. For combined forces and torsion is basically doubly, for H1 is doubly symmetric and single symmetric shape, and that's what we probably concentrate on. So this is when you have both moment and axial. You check them each independently, but you also have to check the effects when both of them are together. And sometimes it depends on the axial load ratio. If this one's less than that, then you only worry about half of the axial load at your moment. If the axial load is more than that, you consider the whole axial load, but you only consider 8/9 of the moment demand. So that's the two, H1 and H2. This is for compression. There is another one for tension later on, and typically for tension is you could account for the C sub B and multiply by that capacity. So you get an increase in capacity for tension because moment plus axial is where you increase the effect is worse. When you're pulling on it, your effect actually gets better by tension. So most of the time is controlled by H1 instead of H2. So typically this section does not govern and is conservative design, and H1.1 governs most design. I skipped over D previously because D is designed for tension. For steel design, the member itself, tension should not be a problem. This is where you have it becomes a problem, where it's at the connection. So I skipped it over the tension for member design, but I added to the end. So something like we have a big web hole or a flange hole, then we actually do check that outside of SAP, because the SAP cannot check the holes, to check tension. But 99% of the time, tension do not govern for steel design. For the members itself, different for connection. But tension is just yielding of the gross section, yielding of the rupture of the net section. This one's ASFY easy. This is the AEs where you have to subtract out the holes to account for that reduced section. Effective area, again, like I said, A net, and then the U. U depends on the shear lag, and these are some of the values you have to calculate in the 360 code. Chapter J, I'll discuss this a little bit more detail, but we will be covering weld, bolts, column base and plate, and then angle rods, as well as flange and web with compression forces. Splices, we're not going to probably have many splices because we're limiting it to less than the 40 foot. So we're going to be shipping the whole column, so no splices to worry about. If you have to do that, then you have to do that. General provision, I will cover it, just in general, but we'll be spending some time in the weld, in the bolt, and mostly in the concentrated forces in the flange and the web. So review. Currently for design, again, just to reiterate it, we only have 16 and 18 for the beam and the column. Not much difference between the two books, the black book and the red book, but we'll do our design if you have it conform to the latest one if possible. For stability design, we'll use the effective link method for calculation of the K. SEP will automatically do a second order analysis, and we'll check that option to include a p-delta analysis. So that's a check. However, one thing we have to do is to add notional loads to the gravity load combination, and that's done through the load combination. I'll show you how to add in a notional load to those load combinations. Remember, for the beam and column, we'll be doing the design using SEP. However, there's some checks that SEP doesn't do, which we have to do separately, which is the holes in the beam and the column. And then for design step 12.2 in the design procedure, we'll have to check that moment capacity, the phi mn, by replacing Zx with the Sx. That's another one. Any questions, or let you guys think about it and recover from your big lunch? Okay, well, I think that's it for, I mean, this is basic design, like I say, is